So today we can continue where we left off, which is the Flownet. Without further ado, I can show you one interesting laboratory test to check what is the Flownet is. This is our earth stem. Here is the water, here is the dry zone. Probably our total head higher at this point than this point. So water will flow from here to here, right to left. How the water flow? This laboratory confirm the way water flow down from right to the left. Wow, blue, red, sipping through this way, this way, this way. Looks like channel. This water only flow through this channel. Do not upward, downward. Just follow this line. Interesting. Now we have come to a very important topic, which is the flow net. It is kind of CP problems. Last week, we considered Bernoulli equation and Darcy's law to calculate water flow through soils. In many instances, the water flow through soil is not one direction only, nor it is uniform over the entire areas perpendicular to flow. In such cases, the water flow in soil is generally calculated by the use of a graphic referred to as a flow net. So from the flow net, by quantifying the graphical solutions, we can figure out the flow line and equipotential line, new terms, flow line, equipotential line. From this net, we can quantify water flow. Flow rate, small q. Q equals to KIA. There should be some K, soil permeability. There should be I, hydrogen loss. There should be A. But at the moment, we don't know this point flow rates. But when you construct this kind of net, you will be able to know. How do you know? Stay tuned. The water flow through soil can be described by Laplace equations. Wow, quite headache. What are equations? This equation quite similar to steady state heat flow. Our heat propagate certain phenomena. This phenomena can be described by some mathematical form. This mathematical form quite similar to, no, actually it is. But in geotechnical field, our researchers just modify these heat transfer equations consisting of total head, x direction, y direction, and z directions. In the heat flow, this H probably hits, but in geotechnical, this is a head. What head? Total head equals to elevation plus pressure head. So this is the popular form of Laplace equation for three-dimensional flow of water. We need to simplify this three-dimensional equation into two-dimensional CVE flow, which is governed by two-directional Laplace equations. Our head, x direction, total head, z directions. As you can see, water can flow x direction and z directions. Can be also expressed by total head and each directions. These two-dimensional flow conditions allow us to use graphical method to find solutions. It is called Flownet. Hi, Prof, you just mentioned that find out some solution, right? What is the solution? Flow rate, also water pressures, even total head. These are what we are going to find from Flownet. Let's take a look at Flownet. This Flownet is basically comprised of the combination of number of flow line and number of equipotential line. New two terms, flow line and equipotential line, to calculate total head and water pressures. So this flow net can be constructed by trial and error. So a series of the trial is necessary with the ultimate aims of drawing a flow net in accordance with all parts comply with the rules. In nature, water flow, and then we can identify the flow directions via some ink, red ink, blue ink, green ink. This is natural. But we need to construct this flow net by our hands in case we need Thom's rule. First one, this flow line and equipotential line intersect each other at a right angle. Most of the 90 degree, 90 degree, 90 degree, 90 degree. Second, the flow elements, the mesh formed at square orthogonals. These elements, the size is the right square, perfect square. So these figures we have seen is the perfect example of the completed flow net constructions. Here, we need to define the boundaries, such as this impermeable rock surface and this shear key, or sometimes our sheet pile. This part is the flow line because water flow through this line, right? Cannot penetrate, cannot break through. That's why these our artificial or nature structures are considered as flow line. And then upstream and downstream surface is the equipotential line because all points on this line has the same total head. This is equipotential line. This line also equipotential line. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 equipotential line. Let's pick up randomly one equipotential line. Let's say this. All point here, 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 here. All are points on this equipotential line has same total head. Hi, prof, is it make sense? It doesn't make sense. No, it makes sense. I'm gonna show you the later. Based on this number of flow channel and equipotential line, we are able to estimate the amount of water flow through the soil as well as for the pressure at any points in the soil. Theoretically, any number of flow line may be drawn, and the greater the number, the more accurate result should be obtained. This is quite, look, for examples, this one more than 20, but our element is less than 10. It means that one element cover 2 meter. 2 meter means more than my height. Very huge. But you draw more dense nets. So probably one element cover 0.1 meter, 0.5 meters. More accurate, but you need more time to calculate, right? That's why we need to find the optimum size of the net, flow net. The flow line is just a line. Water will travel from upstream to downstream in a permeable soil mediums. So water flow this, also flow this, flow this, flow this. The line is flow line. The in between two line is a flow channel. So you can calculate your flow rate for this channel and times channel 1, channel 2, channel 3. So now you can find out total water flow down or flow up. Equipotential line is also line. The total head at all points is equal, which means that if piezometers are placed at different points along the equipotential line, the water level rise up to the same elevation in all of them. If you install this piezometer, the height of water should be same. For example, this height is A. You can install your piezometer here. Your height also A. This point also A. This water height probably B. This water height also B, also B. These two equipotential lines, the difference is A minus B. These differences keep constant. From these, the differences, we can obtain hydraulic gradient, which is the delta H divided by travel length from here to here, probably delta B. Yes. In the flow net, we can find out I, hydraulic gradients, which is the head differences divided by flow distance. The flow net size, unit element size. Again, equipotential line, simply lines, where our total has showed constant values. You see, I put here my the piezometer here. And I also put here same equipotential line. Oh, last slide I gave you the wrong informations. Okay, this is the true. Equipotential line means we have same total head, not the same pressure head. So we set our datum is this line. And then this point we have certain height of the water pressures, which is the pressure head, plus this amount of elevation head. And then this point we have, wow, long height. I mean, high pressure head plus this amount of elevation head. When you set your datums, I think this line of your total head should be same. This is the true. When you set up your piezometer here, the height is the B. This one also B. No, different. Yeah. Can be different. Much higher, much lower. But when you consider elevation head together, which is the total head, that total head should be same on all of the line, along the line. And then this flow line is the path traced by flowing waters. Yes, it is true. So before we dive into more details about some calculations, we need to define some terminologies. It is quite similar to what I just mentioned to you, two different new terminologies. One is the number of equipotential drop rather than number of equipotential line. Here is the 1, 2, 3, 4, 5 equipotential line, but we have different equipotential drop. Later on, we can count. And then, and F is the number of flow channel rather than number of flow line. This line is 1, 2, 3, 4, but channel is 1, 2, 3. And then HL is the total head loss. So the differences of the piezometer reading at a different equipotential line is the head loss, as mentioned before. So let's say the total head loss is HL, and then it is the summation of each head loss at each equipotential line. So hydraulic gradients is delta H divided by delta L, travel length, which is the B, right? Element size. And then the head loss can be represented by head loss divided by number of head drop, number of equipotential drop. So when it comes to calculating our flow channel flow rate, Q equals to KIA. K is the soil's permeability, A is our area. And then I is delta L divided by delta H divided by delta L, which can be also expressed by head loss divided by number of equipotential drop over B. This flow rate for one flow channel times number of flow channel should be total flow rate. That's why we can get this simple equations. You know soil permeability, and then you know head loss. You know number of flow channel, number of equipotential drop, which is our Flownet geometric informations. Then you can calculate total flow rates. So we have two different types of flow nets. When all boundaries to the flow regime are known at the outset, the flow net is the confined flow net. Otherwise, we still don't know some certain phreatic surface. The flow net described as the unconfined flow. So based on our Thom's rule discussed before, we can construct our flow net. Let's sketch up the geometry of our flow net on a natural scale. The ground surface and sheet pile and impermeable layer should be flow line. Water surface here and minimum water surface here, which is the equipotential line. These two lines should be orthogonal here, which is the one flow channel. Start to right angle, finish at right angle. We can keep the same distance. Yeah, one more. We have three flow line. We have 1, 2, 3, 4 flow channel. Then, yes, equipotential line, 2, 3. 1, 2, 3, 4, 5, 6. Equipotential line, but equipotential drop, 1 drop, 2, 3, 4, 5, 6, 7 drops. Then sketch in 2 and more flow line like this. Sorry. An equipotential line. It's more simpler, but your answer sometimes got some errors. These flow nets are not acceptable because the flow line suddenly disappears. And then the angle between the flow line and equipotential line are not right angles. And some of the elements are not square. In this case, this flow net amplitudes some errors. That's why we need to follow the Thom's rule. Hi, Pro, how can we draw all the flow nets by ourselves? The one case should be good enough because we are learning journey. But in design consultant firm, really use this flow net and each engineers draw the flow net. Yes, draw the flow net using.
Hello everyone and welcome to
software
Plexus. So today we're gonna see the variation of the flow through a dam. But before I start, if you're into civil engineering and you love learning, this is the right channel for you. Subscribe to stay tuned. So this is the tutorial, it's tutorial number 10. It's flow through an embankment. So we're gonna see the flow through an earth embankment. It's an earth dam, and see the variation of these flow in the dam. I'll attach a link to this PDF in the description box so you can draw it. So I will tell you that this tutorial is not for beginner. It's an advanced tutorial. If you're a beginner, you should watch the first tutorial I've made to learn how to draw these models, because I will not draw it in this tutorial. So this is the input, the general settings, the model, the borehole model type. We've made here 4 boreholes to obtain this profile of the dam. And this is the material. And then we're going to generate a mesh and create a flow. So here is the 4 borehole, 1, 2, 3, and 4 to create.
This is the plexus settings.
This section of the dam. We haven't drawn anything. We've created a mesh. This is the flow condition. We've created a global water flow with a global water flow like this. So it's created also through the dam here, the water head, through the boreholes. Okay, so we'll do now the calculation. We have the initial phase, phase 1 and phase 2. So on the phase 2, we're gonna select here, select line, water boundaries, we're gonna select them like this, and we've choose them here. We set the behavior to head and set the
essential function are similar to what you learn in graphical communications modules. And just looking at the way we define the boundary condition, the way we create certain flow net. In this case, we can call it a mesh. Let's continue.
Reference as 4.5, so this is 4.5. And we've created the head function, so it's a harmonic signal dropdown. So it's an harmonic variation in the water. It comes from 0 to 1 to -1. So here we can see the head function. It's a harmonic signal. So this is the variation of the water head per day. And then we've made the calculation, so I'm gonna go and check the results.
Yes. This is a finite element mesh. So we also name this kind of software as finite element method. Each element calculate the water flow rate and water pressures and pressure head, total heads. This is quite similar to our Flownet. So let's continue. We can see the certain output from that each element.
So first of all, we're gonna see a cross section. Okay, so for the cross section, we're gonna create an animation of the dam. So we're gonna go to pore pressure groundwater head and go to create animation in file. So let's see how we're doing. Groundwater, pore pressure, groundwater head, and I go to file, create animation, and I choose which phase I want. So to spare some time, we press on OK. I've made already an animation. So you can see here the variation of the water head. You can change the speed of it, of course. And now we're gonna create also a cross section. So the cross section is at 2, 3, 20, and 1 to see the pore pressure in it. So let's go. We're gonna go to tools, cross section, 2, 3, and 20. We've created a cross section. This is the cross section. I'm gonna go stress, pore pressure, active pore pressure. We can see the pore pressure here. So now I'm gonna go to tools, cross-section curves. I'm gonna choose phase 1 and change it from last step to individual step. Here we can see each and every step of the pore pressure with every phase. This is phase 1 at t equals 0.2 days, and these are the variation.
Don't worry too much. In our next geotechnical module, geotechnical engineering, you are supposed to learn this Praxis software. In these soil mechanics modules, we adapt MyDAS software. So this afternoon, their technical support team from India join our tutorial session online, then deliver how they simulate the consolidations. This is the typical example. I'm not gonna go through the details, but simply explain how to address these situations, these problems. You can find out the boundary and the given conditions. Then definitely you can draw this simple version of a Flownet. And then you can count on number of flow channel, number of equipotential drops. And then we can calculate small q, KIA, but in this Flownet, we have a certain specific equations with the incorporation of our Flownet geometry conditions. Then you can simply get certain numbers of the answers. So you may want to consider this equation examples at your home, and then you can discuss further in our tutorial session. Not this week tutorial session, and next week. So this is the simple configuration of our earth stem. And the water flow, groundwater flow, groundwater location is something like that. And then gradually decrease depth. And off the top of my head, water flow to the left to right. And then your stem pipe at certain point, you have certain readings. And then we assume that this is our datums. From here to here, our total head. Here to here, total head. Here to here, total head. Gradually decrease. Our total heads decrease, right? That's why our water flow left to right. So it means that simply you don't know where is your datum, but you can simply install your stem pipe somewhere. You can lead off the water height of the stem pipe, which is a pressure head. This pressure head, the locations, actually not pressure head, because these pressure heads from here to here is much higher than this, right? 19 meters and 15 meters, 34, but only this 26. Pressure head is higher than this, but the typical, the ground water level of the stem pipe inside is higher at a point A. So you can directly read off the location of the water. You can identify the total head. So this is the last topic, but the first topic for our boiling quick conditions issues. The energy transfer takes place from the water to the solid particles, and then forces and the corresponding to the energy transfer is called CPG force. Sometimes this CPG force causes instability of geotechnical structures when the CPG force exceeds soil's effective stress. Mostly the downward seepage increases effective stress, but upward seepage make our soils lower effective stress. This phenomena will deal with the soon in terms of our speed force and effective stress.